All right, welcome to Chapter 3, Section 3.1, defining the derivative. All right, so we have made it through limits. We've made it through the basic idea of what those mean. We know about functions. We know all of this important stuff. Okay, so now we're going to actually get into what calculus, the meat and potatoes of Calculus 1 is all about, and that is this fantastic thing called a derivative. Okay, so the derivative is really going to be about the slope, right? The slope, we know slope, of a tangent line, okay? So we've discussed how to calculate slope, and we've done that of a secant line. We call this the average rate of change. All right, we did this in Math 171. We did this earlier in the first module for us, the average rate of change. Okay, so if you know two coordinate points on a function, you can find their slope. All right, if you connect them with a line, it's called a secant line. All right, so this is the slope of the secant line. All right, so to do this, we'd have to plug in 4. We'd have to plug in 4.5. All right, so f of 4, I'm plugging in 4 to this thing. And then I am plugging in 4.5. I am struggling with my keyboard. I am sorry. Oh my gosh. All right, 7.75. All right, so the idea at 4 and at 4.5, I was originally at 5, now I'm at 7.5. It's a quadratic. So, I mean, the graph should have just done it this way. That would have made so much more sense. All right, so I have this quadratic. All right, I was starting at 4. All right, and then I'm going to 4.5. All right, so I'm going from there to there. Now, if you just look at those two and connect them with a straight line, all right, we're talking about the slope of that thing. So to find that slope, we do the the slope of our secant line, m means slope, 7.75 minus 5 over 4.5 minus 4. Subtract your y, subtract your x's. So 2.25 over 0.5. And we've got a slope of 4.5. Okay, great. Now, one other thing that we might use, and you should have seen this before, is this, I guess, difference quotient. Now, it does the exact same thing. It just kind of changes it up a little bit. Instead of doing f of b and f of a and then doing b minus a, we do f of a plus h. So we just add a little bit to the a value. We subtract f of a and then divide by how much you subtracted. Okay, so if we think about this, this would be f of 4 plus 0.5, which is 4.5, minus f of 4 over just 0.5 So the math is exactly the same. F of 4.5 was 7.75 minus f of 4 over 0.5. All right, so produces the same exact thing. The difference quotient and the average rate of change, they are exactly the same. It's just a matter of, do you want to think about these as two separate points, all right? Or do you want to think about it as you start here and then you just move some distance over and then find another one, okay? So what do you want to be in control of? Picking a point or picking the horizontal distance, okay? But in general, the two ideas are exactly the same. All right, now limits, what we just took a test on, allow us to go from 2 points that are, 0.5 apart to just making that distance that these two things are apart much, much, much smaller. Okay, we make that limit value, that distance between the 2 points, we have them approach each other. Okay, so we do the limit as x approaches the a value or as h approaches 0. Okay, and this then goes from a secant line, two separate, very far apart points, to basically the same point. Okay, so it goes from two different points on our graph, okay, a point here and a point way over here, to now 2 points that are almost precisely the same. All right, and that is the general idea. So here's how we do this. We do, I guess it becomes a tangent line. All right, they're basically the same point. So we have what's called a tangent line in mathematics. So we do the limit. I think I just need to make this much smaller. As x approaches 4, we just put our f of x function minus f of 4. What was the value of f when x was equal to 4? Well, that was 5 over x minus 4, our a value. All right, so we want to try to do this limit. All right. Well, if I just try to plug in 4 minus 4 is going to be 0 on the bottom. I know I can't just direct evaluate. So we try to see what we can do. On the top, I see a 1 minus a 5. That's minus 4. The top of this, I think, can factor. That'd be what? X minus 4, x plus 1. And that is fantastic. Those 4s will cancel. So we are just left with the limit as x approaches 4 of x plus 1. Plug in 4 now, we can do. So 4 plus 1 is 5. All right, so the true slope of our tangent line is 5 right here. If you make those 2 points really, really close together, we get 5. All right, the other version of this, we'll do it the same exact way, just not the same way, a similar way, but very different. Same answer, but very different. So this one, we're doing the limit as h approaches 0. We do f of a plus h. So that means wherever I see an x, I have to put a, which is 4, plus h. Minus f of a, and we said that was 5. And then we just divide by h. All right, so these two methods do the same thing, just very different. This one's good if we are good at factoring. This one's good if we're really just good at multiplying. So why I say that is if we do this one, we have to distribute this. Okay, so we have to do 4 plus h times 4 plus h. We should know that we have to do 4 times 4, that's 16. 4 times h is 4h. H times 4 is 4h. So plus 8h plus h squared. Distribute that 3. And then the +1 and the -5 can make a -4. All right, do we see anything that can combine here? Yeah, I see a 16 minus 12. That's 4. 4 minus 4 cancels. I then see a 8h minus 3h. That's 5h plus h squared divided by h. All right, now I see something good. All of these pieces still have h in them. So it would be 5 plus h. The h would cancel here. H squared is h times h, so one of them would cancel. So that's where I'm getting this 5 plus h. Now I am allowed to plug in 0. I couldn't before. I couldn't just plug in 0 here. But now I can put in 0, and again, I get 5. All right, so the slope of my tangent line is 5 at this spot of x equals 4. Now what this allows us to do is now make it an equation, a straight line. We should remember point slope form from way back when. So y minus y1, that's like y minus f of a is equal to mx minus a if we use our current letters. So it would be y minus the y value, f of 4 was 5, equals m, our slope, which was also 5, times x minus a, which was 4. Distributing would be 5x minus 20. Adding the 5 to the other side. And we get this equation. All right, so putting these two things together, we had our original function. Now if I graph 5x minus 15, and I graph these two, take a look. You see we have our original function, and then you have this next line. Now, these two things are tangent to each other. They will touch at exactly one point, and if we are able to zoom in at that one point, it would look like they are perfect straight lines with each other if we zoom in really, really, really closely right there. Actually, Desmos does a really good job of this. All right, x squared minus 3x plus 1, and y equals... Okay, so these two things should... Oh, I didn't put my dot. There it is. All right, these two graphs, they cross exactly at that one spot, 4, 5. That's where they intersect. All right, and that straight line, that tangent line, compared to the curved graph, if we kind of zoom in at that spot where they cross, we'll kind of see that the curved graph and the tangent line, they start to perfectly line up when you zoom in on that spot. Okay, if you zoom in close enough, you can't even tell that the curved line was even a curved line. It just looks like the straight line. All right, and that is kind of the general goal, I must say, with derivatives in general. Derivatives tell us the slope of this line, but then when we make the tangent line, it allows us to go from curved graphs, all right, that are usually really hard to work with. Especially, I mean, it's a quadratic. It's not super hard to work with. But if it was much larger, if it was a cubic, a quartic, a sine or a cosine, if it was something weird, it turns something weird into potentially just a straight line. And we love working with straight lines. Straight lines are so easy to deal with. All right. And that is kind of one of the big points of calculus, to turn non-linear things into linear pieces. Now, the big picture idea is that we can do these little tiny tangent lines. If we want to, we can turn an entire graph into just little tiny pieces of straight lines. All right. and then we can use those little straight lines instead of the big curved line. All right, it would be very tedious to do all of that, but sometimes it's a lot easier to work with little pieces of straight lines than a big piece of a curved line. All right, and that's kind of what calculus does for us. It finds the little tiny straight line pieces. All right. In general, again, a derivative finds the slope of that tangent line. All right, so we're finding this slope value. And it will always kind of change as you move that value of a. Now, where am I at? There we go. All right, so we have two more. Two more examples. A few more examples. Ooh, we got a bunch of examples. I forgot what's in my own notes. All right, so we have a special notation, a derivative. If we know f of x is our function, then if we do f with a quotation mark, not a quotation mark, an apostrophe, I can say this correctly. If we do f with an apostrophe at a, that means the derivative at a. Sometimes you'll see the phrase f prime. All right, the prime means derivative. All right, so we want to find the derivative of our function f at that coordinate point a. All right, so we have f of x equals 3x squared plus 5x minus 2. And we want to find the derivative f prime at -1. That means our a equals -1. All right, we have two methods. All right. And in general, the two methods produce the same answer, just in slightly different ways. All right. So I'm going to show you both methods. You kind of will have to go back and forth between the two. They both have pros and cons, and so we kind of work with them. We work with both kind of depending on what the problem is. Once you figure out one a little bit better, maybe you use that one a little bit more often. But one of them is the H method, is a little bit better for a lot of different points. The x equals, or the x minus a method on the bottom, is really good if you just have one spot. Okay. All right, so let's see what we can do. So method one, that's the average rate of change method. Method two is the difference quotient. All right, so we're doing the limit as x approaches -1. So on the bottom is going to be x minus -1. Okay. Now we have to do our f of x function, 3x squared plus 5x minus 2 minus the value of the function at -1. All right, so we just plug -1 in here. Okay, so that's what? 3 times 1 minus 5 minus 2. So 3 minus 5. 3 minus 5 is -2, minus 2 is -4. Okay, notice the double negatives will change to positive on the top and the bottom. All right, the -2 and the +4. Made +2. All right, and then this should factor. If it's a polynomial, every single time it should factor. Okay, it should. If it's a really big polynomial, we have some other methods that we can do. Do you remember this thing called synthetic division? Okay, so if it's really big and you can't seem to factor it perfectly, maybe try synthetic division, and that should work. But this one does factor. 3 times 2, that's 6. So what multiplies together to get 6, adds together to get 5. 2 and 3, that's convenient. So my factoring method, I would say, I'm going to put this up here. I would say 3x squared plus 2x plus 3x plus 2. I break my 5 into 2 and 3. So that's what? X on the outside, 3x plus 2. I factor by grouping. That's just the way I've always been told to factor. I don't know why that did not go away. And then x, or 1 comes out of those. All right, so my factors would be x plus 1 and 3x plus 2 over x plus 1. Now, every single time, those should cancel out. So now we can just evaluate the limit. All right, I can plug in -1 now because that denominator has canceled out. So 3 times -1 is -3 plus 2, that is -1. The slope of our tangent line is -1. Now, that's just convenient that that is the same as that number. All right, coincidence, not a guarantee. All right, using the difference quotient method, that's the limit as h approaches 0. All right, we take our big polynomial and we plug in our a plus h. So -1 plus h squared plus 5 times -1 plus h minus 2 minus the f of a. What did we get when we plugged in -1? We got -4, and then we divide by h. Now again, we can't just plug in 0 right away. We'd wind up with 0 in the denominator. Can't do that. So we have to try to simplify. All right, minus negative becomes positive. We have to square this, multiply it by 3, distribute that 5. All right, so let's get after it. Limit as h approaches 0. To square this thing, all right, -1 squared, that's positive 1. -1 times h is negative h. H times -1 is negative h, so that's minus 2h plus h squared. Distribute that 5 and combine those, that's plus 2. Distributing this 3, I'm going to kind of cheat here. 3 times 1 is 3 minus 6h plus 3h squared. All right, I'm going to save myself a line. So the 3 minus 5 is -2, plus 2 means the whole numbers are going to cancel. -6h plus h, that is -h, plus 3h squared over h. And let's see, everything has an h. That's great. So those can all reduce. Don't need my fraction anymore. It would be what? -1 plus 3h. And now we can make h equal to 0. It's not in the denominator anymore. So our limit is just -1. Great. So both answers are the same. That is very, very good. All right, so actually let's take a look at a Desmos graph and see how we feel. It was what? 3x squared minus 5x plus 5x minus 2. Okay, so we have this equation. Okay, we're looking when x is -1. Right here. Okay, notice that -1, we have that y value of -4. That's great. So the idea that we're looking at is what would be the equation, the slope, I should say, of our tangent line if you were able to draw a line that just touches right here at -1, -4. All right, just touches that graph. All right, and just hits the outside of it. Well, I think it would look kind of sort of like this. All right. I think it would come just down and to the right, just like that. So what we're saying is that the slope of our function right here is -1. All right. Both methods gave us a slope of -1. So we're going to find the line that's tangent at -1. So we do y minus our y value. That was -4. Equals m. We found our slope, -1. X minus our x value, -1. Negatives become positive. Double negatives become positive. Distribute our -1 minus the 4. And we have an equation of our tangent line, -x minus 5. So when I finish this, it should produce that tangent line, all right, that touches our graph exactly at -1, -4, all right, and is at perfect tangent. And look at that, just like we thought. All right, it's just at that one spot, and that is a good tangent. Again, big picture calculus idea is that it turned this curve graph, at least for a little while, into this nice, good straight line approximation. All right, that is going to be a big idea that we deal with in calculus all the time. Being able to create linear equations for non-linear functions. All right, so that is great. The slope of our curve, a linear slope at just one precise point. All right, so we're going to keep going here. We've got x cubed. This one seems easy, at x equals 2. So find f prime, the derivative, the slope of the tangent line at x equals 2. Well, I need to know f of 2 cubed, that's 8. Great, so using the average rate of change method. So we do x cubed, our function, minus our value over x minus 2. All right, so for this one, that is a cubed graph. So we have one of two choices. You can either know, that's always fun, you're just supposed to know things, that is called a difference of cubes. All right, so that factors, all right, a difference of cubes becomes x minus whatever the number is cubed, x squared, 2 times whatever, actually you just multiply the 2 and the x, so plus 2x, and then you square that number, so plus 4. That is just the rule for a difference of cubes. There's also a rule for the sum of cubes. Sum of cubes, this becomes plus and this becomes minus. That's just a rule. It's a factoring rule. I don't know how much of that you know, but it's a factoring rule. Those will cancel out. We can then plug in 2. All right, so 2 squared, that's 4, plus 2 times 2, that's 4, plus 4. So 4 plus 4 plus 4 is 12. Our slope here is 12. All right, if you have no idea what a difference of cubes is and that doesn't work for you, here's what I was talking about. You could try synthetic or long division with this, okay? So instead of a difference of cubes, remember putting the opposite of this number in a little box? We would then say 1x cubed, 0x squared, 0x minus 8. Bring down the 1. 1 times 2 is 2. Add, you get 2. 2 times 2 is 4. Add, you get 4. 4 times 2 is 8. Add, you get a remainder of 0. So it was 1x squared, 2x, and 4. All right, so that synthetic division should work every single time with our limits, and that is kind of a fun fact. All right, so we can use that. That is totally fine, and that's good. All right, the difference quotient method. All right, we say the limit as h approaches 0 of h on the bottom. So our x value, 2 plus h cubed, minus our y value at 2, and we have 8. All right, so the hard part here is that we can't just plug in 0. All right, we'd have 0 on the bottom. So now we have to cube this thing. All right, so we have to do 2 plus h, 2 plus h, 2 plus h. So that's what? 4 plus 4h plus h squared. 4 times 2, that's 8, plus 4h. 4h times 2, that's 8h, plus 4h squared. H squared times 2 is 2h squared, plus h cubed. All right, and then this minus 8 and that 8 are going to cancel. I'm trying to do a couple things at one time, shorten up this video. All right, so what do we got left? I see h cubed. I see 2h squared and 4h squared. That's 6h squared. 8h and 4h, that's plus 12h, all divided by h. Great. All of these things have h, so now that h and that h can make that a 2. That'll cancel, make that a 1. That'll go away. Now we can put in 0. Well, if that is 0, that's 0 plus 12. And we have that same answer. We've got 12. All right, so our tangent line at x equals 2, y minus 8, our y value, equals our slope, times x minus 2. So distribute the 12, add the 8, and we are here. All right, so let's just check that in a Desmos. All right, our first graph was x cubed. We're at the coordinate point 2, 8. And then we just said 12x minus 16. All right, so we're looking up here at this coordinate point, and look at that. Good. I feel confident in my solution. I have a good tangent line at x equals 2. All right, my tangent line and my function match up great. And I've got the slope, the average rate of change, all right, at that point 2 was this wonderful answer of 12. Okay. All right, so next one, a square root. All right, so if we do f of 4, square root of 4 is 2. Great. So limit as x approaches 4 of x minus 4. We do the square root of x minus the y value. All right, can't plug in 4. Get 0 on the bottom. We had a rule that said, hey, the ones with square roots and things like that, you multiply by the conjugate. So under the square root of x minus 2, you multiply by the square root of x plus 2 to the top and the bottom. Square root of x times the square root of x is x. Square root of x times 2 would be 2 square root of x. Negative 2 times the square root of x is negative 2 square root of x, so those are canceled. And negative 2 times positive 2 is negative 4. Now on the bottom, we just have these two things multiplied. And if you did your limit homework, you will remember that. Those will cancel, so that is a 1 on the top. Now you can plug in 4, 1 over the square root of 4, which is 2, plus 2. We've got 1/4. All right, the H method does the same thing. If you thought that was confusing, the H method is going to be equally confusing. So we have the square root of our A plus H minus our value. That was just 2. All right, so again, we'd have to multiply by the conjugate. There's no getting around that. All right. The square root of 4 plus h times the square root of 4 plus h is 4 plus h. Square root of 4 plus h times 2, 2 square root of 4 plus h, minus 2 times the square root of 4 plus h, minus 2 square root of 4 plus h, so those would cancel. Negative 2 times 2 is minus 4. On the bottom, we just leave it. The plus 4 minus 4 are going to cancel. The h and the h are going to cancel, reduce to make a 1. So we now have 1 over, I can put 0 in for my h now. The square root of 4 plus 2. Square root of 4 is 2, plus 2 is 1/4. All right, so the square root function should have a slope of 1/4 at x equals 4. So our tangent line y minus our y value equals our slope, x minus our x value. Distribute to 1/2. Add that to 1/2 x minus 2, but then plus 2 is just going to make 1/2 x. All right, let's double check it. Ooh. Ooh, 1/4 x. Did I mess that up? Where did I get 1/2 from? 1/4, it's staring me in the face. So it'd be 1/4 x minus 1, and we add 2 to that. That's a plus 1. I am sorry. 1/4 x plus 1. And there we go. That looks better. Our tangent line, our square root graph, they meet perfectly at 4, 2. Good. This is why we double checked ourselves. All right. And we've got that. So the slope of a tangent, slope of a square root graph when x equals 4 is 1/4. All right. So that's fun. And it does produce that perfect tangent line right there. So we can turn a square root graph into a straight line. All right. Now, one thing that we get to, and I don't want to jump the gun too much, is that in general, these tangent lines can just help us do some things. For instance, let's say the square root, I'm just going to choose an easy one here, of 4.2. All right. So here's what we do with this. The square root of 4.2 is this very not fun number. Before we had calculators, now I know that this statement doesn't make sense nowadays, but before we had actual calculators, to do the square root of 4.2 was extremely difficult. To get this answer to be this accurate was very hard. 4.2, I see on my Desmos, is right there. Well, take a look at our purple, my graph is purple tangent line, and my red square root graph. They are not very far apart. They look almost identical. So if I do 1/4 times 4.2 plus 1, notice those two answers are extremely close. I mean, this rounds to 2.05 extremely easily. That's not a big stretch. Those two answers are super, super, super close. All right. And this is very easy to type in and do. I can do this in my head. All right, 1/4 of 4.2, that is what, 1.05. Yeah, I can do that in my head. Plus 1 is 2.05. All right, so to be able to do some calculations of very difficult numbers and get them pretty darn close without having to do something super crazy was very, very, very useful pre-calculators and still useful today. All right, still going here. All right, so we have another very strange function. We have a rational function, 7 over x. So that's going to be a function that kind of makes one of these weird rationals. Now, x can't be 0. That's not in the domain. But we're not talking about 0. We're talking about at 3. So 7/3. Okay, so our tangent line, our derivative, f prime at 3, as x approaches 3, you have x minus 3 on the bottom, 7 over x on the top, minus 7/3, our value. All right, to simplify this one, we did some of these. We need a common denominator. So this one I have to multiply by x. This one I have to multiply by 3. I hope that everybody's okay with that. Multiply the top and the bottom of a fraction is a-okay. If we did our limit work, I hope we did our limit work and didn't skip over those videos. So 7 times 3, that's 21 over 3x minus 7x over 3x. Now these two have the same denominator, so we can just make it one big fraction with 3x on the bottom. We do same change flip. So it's like that over 1, a fraction divided by a fraction. So we have 1 over x minus 3. What we learned is that this thing, or this thing, we can factor and rearrange. Okay. Now I see what 7 goes into both, and I can even factor out a negative 7. That would be x minus 3, which allows these to cancel. And therefore all we have left is just negative 7 on the top And 3 times our x on the bottom, we're going to make x equal to 3. So 3 times 3 is 9. All right, we have our slope at x equals 3. All right, method 2, the a plus h method, difference quotient. Is going to be a little messier. I know that's a hard statement to put up with. But these, I can't just add an h at the bottom. So the only method is to multiply this one by 3, multiply this one by 3 plus h. All right, so we wind up with similar things. I hope that made sense. 21 over 3 times 3 plus h minus 21 plus 7h over 3 times 3 plus h. Same denominator, so we can subtract the numerators. 21 minus 21 cancels. Great. So I just have 7h over 3 times 3 plus h. Again, we can do same, change, flip. Cool. Our h and our h will cancel. We can now plug in h equals 0. 7 times 1. Ooh, now I'm a little worried. Oh, it was a minus 7h, sorry. Minus this 7h, that made that negative. So we have negative 7 over, h is 0 now, right? So 0 plus 3 is 3. 3 times 3 is 9. All right, so our tangent line, y minus 7/3 equals negative 7/9. That's minus 3. Distribute your 7/9. This is not going to be pretty. What the 3 and the 9 would reduce. I already got the plus. 7/3. Add another 7/3 to that. And we have that wonderful answer, negative 7/9 plus 14/3. All right. Now, in general, not fun functions like that are going to have not fun answers like negative 7/9 x plus 14/3. All right. Not fun answers get, not fun questions get non-fun answers. That is just the rule of math in general. But hopefully we are good with that. I see a tangent line. I see that rational function. All right. So to turn that rational function into a straight line for just a little bit, not nearly as fun, but useful, okay, in its own right. All right. The derivative is also called the instantaneous rate of change. Okay, so that's something you might see. We had the average rate of change, or just the rate of change. So this is called the instantaneous rate of change. All right, how is our function changing precisely at that point? All right, and we can even use graphs to estimate these. Okay, so I have a graph. We can use the graph to estimate. So at -2, -1, -2, right here, estimate the slope of our equation. Estimate the slope of that graph. Well, it looks like it would be this. I think the slope here would be 0. Okay, that's cool. F of -1, -1, f prime of -1 is here. Well, I think that one's also 0. F prime at 1. Oh, hey, I think that's 0. That's a flat line. F prime at 2. Yeah, I think that's also a flat line. All right, all of these are equal to 0. Okay, that's really cool. But the thing about that being 0, look at all 4 of those points. Those are the maximums and minimums. The maximum and minimums have a slope of 0. That's actually going to be how we, with calculus, can calculate where a maximum or minimum, where an extrema occurs. We can do it based on its derivative being equal to 0. That's going to be a huge, huge, huge factor of these things as we move forward. All right, some not as easy ones. Let's see. Let's calculate our slope at x equals 0. Let's see. If I had to make this tangent line, I can kind of follow that. I would say maybe it goes up 3 over 1. That made sense to me. At 1.5, we're here. If I kind of follow this down, that would be a good spot. It's like down almost 2 over 1. So I'd say it's close to -2. All right, at -0.5, that's here. If I follow my equation up, I mean, I'd probably say that's pretty close in line with this one here. I'd probably agree that that's still maybe 3 at 0.8. So 1, 2, 3, 4. So that's here. That one's a little bit shallower. So went from a 0.8 to, that would be tough. I don't like that. Well, let's see. Let's just count little blocks as we go. I think that might even be like an up 1 over 1. That might be about a 1. All right, if I'm counting from that block to that block, and they are the same ratio, and they are, I can guess that's about a slope of 1. Yeah, that makes sense. So we can use the graph to at least give us an estimate. All right, we can know if the graph is, or if the derivative is at least positive or negative. Is the graph going up or down? That's super easy. We can find when they're 0 relatively easy from a graph, those maximums and minimums. So we can get decent estimates. All right, really steep would be a very high positive. All right, this would be a negative slope. So that's just kind of nice and useful. All right, so last question here. Maybe pause it real quick. See if you can guess these things as for before I do them. The slope at -4, f prime at -4, f prime at -2. All right, -4, 0. F prime at -2, I would say 0. F prime at -1 is positive, but less than 1. I don't think that that's an up 1 over 1 situation. I would say maybe a 1/2. At 0, I'm thinking 0. At 2, I'm definitely thinking 0. At 3, it's negative. It's looking like it's maybe down 2 over 1. At 4, 0. At 4.5, maybe like a positive 2, up 2 over 1, somewhere in that zone. All right, at least a broad guess. All right, so again, we can find these things very, very precisely, all right, using those two limit definitions, either one, or we can at least get a decent estimate solely based on a graph. All right, so that is the basics of derivatives. Whew, that's a long video. Good luck on that work.